Hi, my name is Robin. I wrote my essay on the different designs of quantum computers. This presentation, however, will focus on the two most developed of those, that being the ion trap and the superconducting. This is because IBM has actually built a working ion trap computer, and Google has built a working superconducting computer, making these two designs the only two designs that have actually been built and proved to be working. I will do this by first explaining very briefly what quantum computing is. Then I explain in more detail what ion trap technology is and superconducting technology, and explain how they are used for quantum computing purposes. Finally, I will highlight the superiorities of both and identify which is the most promising one in my conclusion. Now, what is quantum computing? Well, just as classical computing, it uses ones and zeros, but it utilizes something called quantum state theory, which says something can exist as a superposition of two or more definitive states. So instead of being just 1 or 0, it's 1 and 0, and both at the same time. Then you create a qubit, which is the same as a regular bit for classical computers, except for quantum computers. And to create a qubit, you need three things. You need a superposition of some sort between two definitive states. You need them to be able to affect each other so that you can apply function and logic to the system. And you need to be able to deliberately change it from the outside, or else you'll have no way of influencing or doing any computing. If you can fulfill these three criteria, you have a working qubit. Now, ion trap technology fulfills these three criteria like this. They trap ions, which are charged atoms achieved by removing or adding electrons, thus making them subject to magnetic fields. So you trap them in a three-dimensional magnetic field as seen on the screen, then you cool them down so they become still enough to individually hit with lasers. Now the superposition here, well, the ion, the spin direction of the ions exists in a natural superposition state, and this is the spin direction that you use as 1 and 0. They affect each other by something called an ion vibration chain, which is a quantum mechanical phenomenon where two ions are able to affect each other even though they're not really connected. We don't know how it works, but we know that it works, and so we can use it. Now, as for deliberate change, well, if you can hit them with lasers, you can add just enough energy to flip the state on purpose. Therefore, you can affect the system. And it therefore fills all the three criteria and are a working qubit. The superconducting qubit works very differently. Superconduction is when there is absolutely no electrical resistivity in a conductor, and it occurs at very low temperatures. When superconduction occurs, electrons they bond together in pairs. When the electrons bond together in pairs, they effectively become a boson. A boson has the quantum mechanical property to be able to tunnel, or quantum tunnel. That is the act of sort of tunneling through a physical barrier that they really shouldn't be able to do, but they can because of quantum mechanics. Now you then create a Josephson junction, which is basically two plates, superconducting plates like this, separated by a thin layer of non-conducting material, or a physical barrier. You then cool this system down so that the superconduction occurs, and then a small current will start flowing because the electron pairs are tunneling through the layer in here and then circulating around. There is no voltage at this point, but this current will slowly increase and increase until a voltage is created. Now this voltage will be an AC voltage, but unlike regular AC voltages, the change in voltage direction is not periodical, it's completely random. So we use the voltage direction as 1 and 0, where if you go clockwise it's 1 or anti-clockwise it's 0 or whatever. Now, the superposition is achieved by the voltage being completely random, meaning that until we know which direction the voltage is going, it exists in a superposition between both. Therefore, it is a quantum mechanical object of sorts. Now, they affect each other like any other electronics would. You just wire the circuits together. It's still just a circuit, just an electronic circuit. And because it's an electronic circuit, it's very easy to affect from an outside source, like an electric field or a magnetic field, or voltage going through a conductor right nearby. It's very easy to influence electronics. And so it's very easy to put together some sort of system that utilizes all of these. And that is the basic idea of superconducting quantum computers. Now, the ion trap superiorities are, well, there are only two, but they are rather significant. They can be lasered cooled down. Both of these systems, the superconducting and the ion trap, both need to be cooled down to a very, very low temperature. That is very hard for the superconducting because you have to physically cool it down, which is very expensive and very energy costly. But because the ion trap utilizes particles, they can use a trick where they fire photons to collide with the ions vibrating in such a way that when they crash, the momentum of the collision is conserved, and therefore the vibrational energy of the ion is decreased. Now, by firing these photons at a frequency just below what needs to be for them to actually interact, they make sure that if the ions are moving away and the photon comes up behind, it won't interact, thereby not speeding up the vibrational energy of the ions. But if they're moving together, then because of the Doppler effect, the frequency of the photon will be perceived as slightly larger, therefore being the correct frequency, and they will interact, and the collision will have a decreasing effect on the vibrational energy of the ion. Therefore, by just firing billions and billions of photons at random directions through this magnetic field where all the ions are trapped, you will cool them down by slowing the vibration of the ions down to almost nothing, achieving almost absolute zero very easily. The other thing is coherence. Now, the superconducting technology, the voltage that flips, that occurs, it doesn't last forever. It actually lasts a very, very short time because the current continues to build to the point where the current stops being AC and just starts being a regular current. The longest coherence time as of 2019 in a superconducting circuit is about 0.4 milliseconds, which is not very long. Now, the superconducting superiorities, well, they are cheap to build. They are just completely normal electronic circuits at a very low temperature. It's not expensive at all. It's also very modifiable, as all electronics are. Because it's based on electronics, anything you can modify electronics, you can also modify this. It's again also infinitely scalable, because again it's based on electronics. You can just wire more of them together and you get an infinite scale. You're getting thousands of them wired together, no problem. And it's new, so less of its potential has been discovered. This leads me to the conclusion that the superconducting technology is the superior design. It's more practical, it's cheaper, it's a lot more modifiable, almost infinitely scalable, but most importantly, it's a lot more potential. From 2009 to 2019, the coherence time increased 400 times, with scientists confident that they can tenfold that by the end of 2020, meaning that in a period of 11 years, the coherence time could increase by 4,000 times, which shows significant advantages in this field, significant new discoveries. Also, if you remove all of the problems with the ion trap technology, you get a really good quantum computer. But if you remove the problems with the superconducting technology, you get an absolutely amazing quantum computer, infinitely scalable and pretty cheap to build. It is also the only hope we can ever have of getting a quantum computer chip for regular computers at home. You can never build an ion trap chip, but you can build a superconducting chip, which means that it has a lot more commercial applications as well. These are my sources. Thank you very much for your attention.